Welcome to the Math 1, Unit 8, Lesson 6 summary video, Fireworks. This lesson is a Solidify Understanding task which takes concepts developed previously and helps you formalize those ideas. The purpose of this lesson is to solidify understanding of how the factors of a quadratic function are connected to the solutions and x-intercepts of the graph and make comparisons of key features in different representations. The use of a graphing calculator or Desmos is highly recommended for this task. In today's lesson, you're asked to identify and compare the key features of 3 different fireworks. Each firework creates a unique parabolic shape based on its key features. We will take a look at these features, many of which you are already familiar with due to your previous work with linear and exponential functions. Some of the features that we will be talking about today are the initial height, which will be represented with the y-intercept, the initial velocity, the acceleration due to gravity, which we talked about in a previous video. We use negative 16x squared for the quadratic term of our functions, and this is relative to projectile motion problems. The maximum height, which is the vertex, the time from initial launch until it returns to the ground, and we'll be talking about this in regards to the x-intercepts, the practical domain and range, and the intervals of increasing and decreasing. And so in this problem, we are given 3 different fireworks, glitter palm, Chrisette, and Waterfall, and for each of the fireworks, we're given a different representation. From the given representation, we can then produce additional representations for that particular firework, which we can then use to compare all of the features of all 3 functions. For glitter palm, they gave us the graph that you see on the left. We can use that graph and take some of the information, enter it into Desmos, and that will help us gain more information. So when I look at the graph, one thing that I notice is it's got an x-intercept here of 0, 0. This is also the y-intercept. And so what that tells me is that we know that the y-intercept is the initial height. And so I know that this firework is being launched from the ground. So my y-axis represents the distance above the ground in feet, and the x-intercept represents the time in seconds. So it starts on the ground, and it's launched up into the air. We don't know the velocity with which it's launched, but we know that it takes 3 seconds for it to reach its maximum height. This maximum height, which is just above 140 feet, is called its vertex. The vertex is the point at which the quadratic or the parabola goes from the interval of increasing, which is from 0 to 3, and then transitions to the interval of decreasing, which is 3 to 6. So it's the point at which the parabola goes from increasing to decreasing. And so this is the maximum height, and that's located at 3 seconds and just above 140 feet. We can see that it has 2 x-intercepts, and what that tells us is how long the firework was in the air. So we know that it was launched initially at 0 seconds, and then it was back down on the ground at 6 seconds, which tells us that it was in the air for 6 seconds. Again, with our vertex being at 3 seconds, we know that it took 3 seconds for the firework to reach its maximum height. When we look at our domain and our range, we are looking at this in terms of our practical domain and range. So in the context of the story, the part of the domain and the range that makes sense in context. While we see the parabola goes down into the negative x and y values, we know that those x and y values represent time and distance. Therefore, the negative values would not make sense in this situation. So the practical domain would go from 0 to 6, and the practical range would be from 0 up to just above 140 feet. We know that the acceleration due to gravity, because this is a projectile motion problem, this coefficient of our quadratic term in our function is going to be negative 16. I was able to determine the velocity of the function, and we notice that there is no constant term here. There's no third term to our quadratic because it would be 0. That third term represents the initial height, and the initial height is 0, so it's not necessary to put the 0 in. You are not expected to come up with this equation at this point because we're just learning about quadratics. Eventually you will be. And if we take this quadratic and rewrite it in factored form, we factor out that negative 16 from each of the terms, we're left with these two factors. When I use the zero product property with each of these factors and set them equal to 0 and solve for t, I get the solutions 0 and 6. So the solutions to this quadratic function are 0 and 6. And what that tells me is that those are my x-intercepts. So the quadratic starts when x is 0 because t is our x, is represented on our x-axis. That's our time. So at the time of 0 and the time of 6, our quadratic will be touching our x-axis. When I looked at the graph, I know this point at 0, 0, and this point at 6, 0. I don't know for sure, even though I know the x value for this point is 3, I'm not quite sure what the y value is just by looking at it. And I can see that at 1 second, if I go up, it looks like this is at 80, and at 5 seconds, it looks like it's also at 80. I noticed that one of the features of quadratics is that it's symmetrical on either side of the vertex. And so knowing that, or suspecting that this y value is 80 and the y value when x is 5 is 80, I was able to put this information into my table in Desmos, and it was able to give me additional output values. If I wanted to do this by hand, I could be looking for, I know that common difference is going to be 32 when it's increasing and negative 32 when it's decreasing, that common second difference. And so I can use that information also to help me find these values. One other thing I want to point out, the vertex, the x value of the vertex, you'll notice, is 3, which is halfway between my two x-intercepts. And so again, that supports the idea that the parabola is symmetrical. So from 0 to 3 and 3 to 6, 3 being the halfway mark. If we look at the second firework, this one is Chrisette, and they gave us this information right here. The rocket height above the ground after t seconds is given by this equation. So they tell us that the initial velocity, or excuse me, the acceleration due to gravity is negative 16 t squared. The velocity is 80, and so our second term is 80 t. When I take this standard form and I rewrite it in factored form, factoring out that negative 16 t from each term, I'm left with this factor and this factor. I'm using the zero product property to set them each equal to 0 and solving for my t values. That tells me that I have one x-intercept when t is 0 and another x-intercept when t is 5. And you can see those represented here in the graph and here in the table. I also can take any value, because they gave me the equation, I can take any value, substitute it in for my t here and my t here to get my function of x or t. I can see the practical domain is from 0 to 5, the practical range from 0 up here to somewhere in between. I see that at 2 seconds it's at 96, and 3 seconds it's also at 96. And if I were to put 2.5 into my Desmos graphing calculator, it would tell me that the output is 100. So the vertex here is at 100, at 2.5 seconds. I know it's at 2.5 seconds because it's halfway between the 2 and the 3. So the maximum height is reached at 2.5 seconds. It took 5 seconds for this firework to be launched, hit its vertex or maximum height, and return to the ground. The interval of increasing is the first half of the parabola, and it's from 0 to 2.5. The interval of decreasing is from 2.5 to 5. And when we look at the third firework that they gave us, this is Waterfall. And so for this one, they just gave us this information. It tells us that the rocket had an initial height of 64, and we can see that in our third term here. Had an upward velocity of 48 feet per second. That is our second or linear term in our quadratic. And we know that this is our first term because this is a projectile motion problem. We can then take this function and solve it for t, so we can figure out what our t values are. The first thing we're going to do is factor out the greatest common factor of each of the terms, which is -16, and we're left with this trinomial. We're going to factor out this trinomial, and we get these 3 factors. We're going to set these 2 factors that contain my variables equal to 0 using the zero product property and solve for t. We see that we get t equals 4 and t equals -1. Remember, this is time, so it's saying that the quadratic will intersect with my x-axis at -1 second and 4 seconds. We know that -1 second doesn't make sense in the context of the story, so this is not a valid solution in this particular problem. What this 4-0 tells us is that the rocket will be back on the ground after 4 seconds. So at 0 seconds, it's launched from here, 64 feet up above the ground, and so the practical range is going from 64 up to the vertex, or the maximum height, which is at 100. The practical range goes from domain goes from 0 to 4. The interval of increasing is from 0, now this is 1 and this is 2, so the vertex or maximum height is going to be halfway between that at these two x values at 1.5. And so my interval of increasing is from 0 to 1.5, and the interval of decreasing is 1.5 to 4. I can find the exact value of this vertex because I know that the x value is halfway between these 2 values. And so I know that this is going to be at 1.5. And if I substitute 1.5 in for this t and I simplify, I'm going to get an output, or the function of t, which is 100. And so the next slide is what it looks like when we put all 3 together. And so and again, I used Desmos to do this. And so if you have not worked with Desmos, this would be a great time to become familiar with it. You can also use your graphing calculator to do this, and you can put all 3 functions in so that you can see them on one graph. There are tons of tutorial videos available online if you're not sure how to use either your graphing calculator or Desmos to accomplish this. So here we can see, here's the key that represents each of these functions. We can see that these 2 functions, Chrisette and Waterfall, had equal maximum heights, which was at 100. So their vertex, although it occurred at different times, this green one, Waterfall, reached its vertex faster than the other 2. We can see that Chrisette reached its vertex at 2.5 seconds, and Glitter Palm reached its vertex at 3 seconds. So it was the slowest to reach the vertex, but it also launched from the ground and had the highest maximum height. So one of the big takeaways from today's lesson is the understanding that the x-intercepts for each of the functions are the solutions to the functions themselves. So when we solved the equations that were given, the solutions that we discovered for the variables represent where our quadratic functions intersect the x-axis.